question 6. We have unpolarized light coming in. So I have drawn some oscillations representing unpolarized light. Obviously there are oscillations in planes in between those arrows as well, as it's unpolarized. The polarizing filter transmits light of intensity I. So the intensity coming out over here is I, and this filter is rotated. So this filter would, let's say, polarize in a direction, and let's pick a direction in the vertical plane. Now we can see there is a oscillation in the vertical plane, and that will pass through, and we will get some intensity. We will get some component of these offset rotations, oscillations come through as well, and the perpendicular one will not. And now if I rotate this filter, and there will always be a oscillating plane in line with the polarizing plane. So therefore we will always get the same intensity coming out, and we are making the assumption that the intensity of all of the oscillating planes is exactly the same. So that and that and so on, and all the in-betweens have the same incoming oscillating intensity. So therefore the outgoing intensity will remain as I, because there will always be a oscillating plane in line with the polarizing plane. Therefore the outward intensity is equal to I. It is not 0. For that we need two filters perpendicular to one another for 0 intensity to appear on the exit of the second filter. Question 7, this is a displacement time graph. This is that which of the following statements is not correct? Now time period, we can clearly see that we've got time, and then we can find the time period from either there to there or peak to peak, but it is measurable, that's correct. So it's not, we're looking for not correct. Now I'll go for C and D before I go and talk about B. The wavelength could be longitudinal, the wavelength could be transverse. That's true. It could be longitudinal. Longitudinal waves are represented in displacement time graphs as sinusoidal waves, and transverse waves are also represented as sinusoidal displacement time graph waves. How does that come by? I have just made some additional notes for that. So when we have a longitudinal wave, this picture here, this is a particle there, that dot, and we know that the particles oscillate. I've just picked one of thousands of particles in that wave. So let's look at that. That particle will be oscillating back and forth sideways, and the wave energy is propagating parallel to the oscillations. So oscillations left, right, wave energy parallel to that oscillation. Now if we look at the oscillation, the furthest most left position is your negative amplitude, the furthest most right position is your amplitude, and the position of that particle dead center in between those two positions is your equilibrium 0 position. Now we can plot the displacement relative to 0 on the y-axis, and we can see where that particle is in a given time. So after a time, where is that particle? Is it at the amplitude? Is it between? Is it negative or in between, etc.? Similarly, with transverse waves, we see that the particles move in this scenario up and down, and the wave energy is perpendicular as per definition. So again, that particle The uppermost position is the amplitude, the lowermost position is the negative amplitude, and in the middle is the equilibrium. So the particle oscillates between similar displacements, a max, a min, and through equilibrium. How we represent it as on a graph is very much similar to what the wave actually looks like for transverse, but for a longitudinal, the wave doesn't realistically look like that, but it can be mapped in that way. And then finally, the actual answer: the wavelength can be determined directly from the graph. No, we cannot see. Wavelength will be, if that was distance, that axis, horizontal was distance, and you go from peak to peak. So peak to peak is your time period. From time period you find frequency, and if we wanted wavelength, we'll have to know the speed of the wave and use the V equals F lambda formula in conjunction with this graph. However, we cannot take wavelength from this graph based on the information given. Question 8. I'm going to write down some expressions, as this question discusses density later on. Now, density will be the mass of this object. This is a small cube, and we know that cubes have the same dimensions. So the mass of the cube, 50, divided by the dimensions of the volume, which is x cubed. So that will be the density. Okay, it'll be in grams per whatever unit that value of x is. I'll talk about why I've done this and rearranged it to equal 50 in just a moment. Let's go to the next one. Density of the large cube is 50 over 1.5x. That's the dimension of one of the sides, and therefore you have to cube all that to get 1.5x all cubed. And again, I've rearranged to get 50 equals. Now, because they both weigh the same mass, 50, which that's the reason why I've made them equal to 50, because what we are going to do is compare densities, and to do that we have to look for something common. And the easiest thing to look for that is common is the numbers. You could say x cubed and rearrange accordingly. However, this is another way of doing it. So we have got, this is for your small cube, this is from your large cube, and we are going to equate them because they are both equal to 50. So therefore the density of the large cube times by 1.5 cubed times by x cubed equal density of small cube times by x cubed. And rearrange and tidy up, we get density of the large cube is 1 over 1.5 cubed density of the small cube, and that works out to be 0.3 of the density of the small cube. And this is how we answer this question. Look for similarities between the two expressions, and that was 50 and 50. We see there's no 50 in these, so therefore we're looking to link the two formula. Question 9. We have got a stationary wave. As soon as you've read that, you must be considering everything you know about stationary waves. I've added some annotations along the way. Now it says again, which following statement is not correct? Now, just some first point, all of the points between two nodes, there's one node there, there's another node there, so all of these points along this section here move in sync, i.e. they move with each other. So when the string, this part of the string goes down, this part of the string goes down, this part of the string goes down with each other, so they follow each other. All of the points between two adjacent nodes are in phase, so all of these points are in phase. When this part of the string is moving down, this part of the string is moving up, and all of these points between these two nodes are in sync, in phase with one another as well. So the first part, it says point X and Z are in antiphase. X and Z, when X moves down, Z moves up. That is correct for a stationary wave, as all points here move down when these all points move up. Point Y and Z have the same amplitude of vibration. Now let's look at where Y and Z are. Y has an amplitude from where it is, this displacement, to the equilibrium. And if you look at those two distances from where the displacement is to the equilibrium, they are different. So therefore, point B is incorrectly stated, and that's what we're looking for. Let's just confirm the other two are correct. Z is an antinode. It's sitting halfway between a node and another node, and that is correct. Z is indeed an antinode, and Y and Z have the same frequency of vibration. Every point along this string has the same frequency, i.e. that when this part, let's say Y, goes all the way to its opposite end and then back to its starting position, Z would have done the same thing in the same amount of time. So therefore the time period for one complete cycle and one complete cycle for Y and Z are the same, and that goes for all points along that wave. So therefore B is wrong. Question 10, last question on the multiple choice. You got two springs, S1 and S2. First spring extended by X with mass M. Second spring extended by X over 3 with a mass 2M. Okay, and it says the extension of S1 is X and the extension of S2 is X over 3, and also it says the elastic strain energy is E for this spring. So how do we introduce that into all of this? So we will look at S1 first of all. They haven't talked about force constant, so I'm not going to write down the formula for elastic strain energy, or elastic potential energy in other words. E equals half kx squared. We don't have k given because they're two different springs. We will use a half fx because this is the other way of working out the elastic potential energy. So what is the force on the first spring? It is mg because the mass is m, and that times by g, and then the extension is x also, so we just write x here again, and therefore the strain energy E as written here for S1 is a half mgx. So what we're going to do is do the same thing for S2. So a half of F2 times by X2. So how much force is on spring 2? That's 2m, so it'll be 2mg. And how much is the extension? So the extension is X over 3. So there'll be a half times 2mg times X over 3. Now I'm not going to tidy out those numbers, but the reason I've done that is I'm trying to find a half mgx, and I'm pulling it to a side because a half mgx represents the elastic strain energy. So I have taken that half, taken that m, taken that x, and put it to a side, taken the 2 because I haven't used that, and a third that's underneath the x, I pull that out as well, and I get 2/3 of a half mgx. Well, I know half mgx is equivalent to the strain energy of spring 1. So I've just replaced half mgx with E. So I know that the second spring has 2/3 of the strain energy of the first spring. Now if you look across here, C gives us that answer. What are we trying to do? We've got an expression for S1. We're trying to see if half mgx appears in the second statement, and if it does, we replace it with the letter E as the strain energy of the second spring is expressed in the strain energy of the first.